Hello everyone, my name is Bingyong Guo, a postdoc at the Center for Ocean Energy Research, Maynooth University, Ireland. Today I'm going to talk about the parametric study of a wide-band impact wave energy converter. In this talk, I will introduce briefly the background of this study, followed with the modeling of the wide-band impact wave energy converter. The main focus is the parametric study of this system with some numerical results and discussion. Some conclusion will be drawn at the end. A wave energy converter is designed to harvest the energy from ocean waves and generate electricity. As shown in this figure, a floating buoy is applied to harvest wave energy. The buoy will oscillate under the excitation of the ocean waves. A inner mass, spring, and damper was used as a pole takeoff system to generate electricity. In practice, it can be a linear generator. When the wave is huge, the inner mass may collide with the bottom or the top of the buoy, hence, and protect is required for such a system, which can be achieved by active control or passive design. In this study, we introduce a wide-band impact mechanism, adding impact springs at the top or bottom of the buoy. When the relative displacement between the inner mass and the buoy exceeds the gap G, the impact springs will be active to provide passive end-stop function. Meanwhile, this wide-band impact mechanism can also enhance the performance of the system in terms of power capture. On the other hand, this power impact system may introduce rich and complex nonlinear dynamics, and the system dynamics are very sensitive to the wide-band impact parameters. As shown in this figure, we can see that when we change the gap, the system dynamics change hugely. We can see chaotic motion, multi-period motion, and multi-stability problems. So it's quite important for us to see how less wide-band impact parameters are going to affect the system dynamics and what region of the parameters we are preferred to achieve a simple system with high power capture. That's why we need to do such a parametric study for this wide-band impact system. Before we get into the parametric system, here I will introduce simply about the modeling of the system. The motion of the buoy is governed by this equation. This is the excitation force due to the incident waves, which can be approximated by a state space model with the wave prediction. Wave prediction is required because the wave-to-wave excitation process is non-causal, so we have to use wave prediction to overcome this non-causal problem. The radiation force is causal, so it can be simply approximated by a state space model. For cylinder, the hydrostatic force is simple. Fi means the interaction force between the buoy and the inner mass. The movement of the inner mass is quite simple. It's only governed by the interaction force. However, the interaction force depends on the relationship between the relative displacement and the gap. When the relative displacement is larger than the gap, the upper impact spring is active. When the relative displacement is smaller than the lower gap, the lower impact spring is active. Otherwise, only the mass spring damper works. So this is the system dynamics. Based on the modeling, a parametric study has been conducted to evaluate the system performance. Here we define the relative response amplitude operator as here to represent the system dynamics, and here we also define the instant power and the average power to represent the main output of the system. As we can see from this figure here, the peak value is much larger than the average value. Hence, it is very important to define the peak to average power ratio here. In practice, a large peak to average power ratio always means a huge cost on the PTO system. For this parametric study, we are going to adjust the parameters in a wide range and to see how these parameters affect the system dynamics, which includes the PTO mass mm, PTO stiffness K1, impact stiffness K2, impact gap G, and the PTO damping coefficient C. In this study, we only consider regular waves with wave height 0.8 meters. By varying the PTO mass in a wide range, the contour plots of the relative RAO, average power, and peak to average power ratio are shown here with a wide range of wave frequencies. As we can see from figures A and B, the system is a bandpass filter, and its natural frequency decreases as the inner mass increases. The bandwidth increases first and then decreases. For the average power, we can see that when the inner mass is large, the bandwidth is very narrow. The peak to average power ratio will be influenced when the impact happens. It can be attenuated or be amplified. Of course, this region is not preferred. So to balance these three indexes, the value in this region is preferred. As we can see, we can get a relatively large RAO and average power with a wide bandwidth, and at the same time, the peak to average power ratio is small. By varying the stiffness, here shows the results. We can see that the system is a bandpass filter, and the natural frequency increases as the stiffness increases. The bandwidth increases first and then decreases sharply. So also we can see that the peak to average power ratio influenced by the occurrence of the impacts, especially when the stiffness is small. The peak to average ratio is amplified from 2 to 3. Based on these three indexes, we can see that the stiffness region are preferred. Here we can get a relatively large RAO and average power with a wide bandwidth, and also we can see the peak to average power ratio is not amplified. Different from the other two, we can see that by increasing the stiffness, it only affects the maximum value of the relative RAO or the average power. It never influences the bandwidth or the natural frequencies. When impact occurs, the peak to average power ratio will be attenuated or amplified, but it not depends on the stiffness. It only depends on the wave frequencies. As the impact occurs, the impact springs are active. So, a large K2 is preferred to provide effective end-stop function to constrain the physical motion of the system. By varying the gap, here we can see that the system still works like a bandpass filter, and the bandwidth increases as the gap increases, and of course the maximum values increases as the gap increases, but it never affects the natural frequency. The very interesting thing happens here. It has a huge influence on the peak-to-average ratio, especially when the gap is small. To say, when the gap is smaller than 0.2, the peak-to-average power ratio is amplified from 2 to 7. In this case, there are several impacts happens in one wave period, which lead to a huge ripple in the power generation. So in this case, we can see that the gap G is one of the most critical parameters because it can determine the occurrence of the impact directly. Based on these three performance indices, this region is preferred. So we can have a large relative I/O, but not as large as to cause some collision. And of course, we can have a large average power, and the bandwidth is quite wide. Meanwhile, a small peak-to-average power ratio can be achieved. And of course, we can adjusting the PTO damping coefficient. The system performs like a bandpass filter, and the damping only influences the bandwidth and the maximum values, and it never influences the natural frequencies. In the figure B, the bandwidth are going to be increased, and then the peak value increase first and then decrease. It means that there will be always an optimum damping to achieve power maximization. For the peak-to-average power ratio, it can be amplified or attenuated. To make a balance, we can say that this region is preferred. We can have a large I/O and a large power capture, but the peak-to-average power ratio cannot be amplified too much. Based on the simulation, here we can summarize the study. The relative I/O is characterized by a bandpass filter no matter how we design the variable impact parameters. The average power output is sensitive to all the design parameters, and the peak-to-average power ratio is only affected significantly by the impact gap. The bandwidth and the natural frequency is sensitive to the PTO mass and stiffness, but insensitive to the impact stiffness, impact gap, and the PTO damping coefficient. This parametric study can give some basic guidelines for the design and optimization of the variable impact VAC. In this study, we only consider the regular waves, and ongoing work focus on the parametric study of the variable impact VAC in irregular waves. Here, I'm very glad to show you some information. We have a special issue launched in the IET renewable power generation with specific focus on wave energy conversion. The topics including the modeling and control, fluid dynamics, testing of PTO systems, tank testing, multifunction offshore platforms, energy storage and grid integrations, and power resource assessment and everything related to wave energy conversion. The deadline for submission is December 1st, 2020. This project has received funding from the Marie Curie grant. Special thanks are given to the financial supporting from the H2020 program. Thank you for your attention. If you have any questions, you are very welcome to ask now.